Alright, so next up we're going to move on to section 3.3 and the dot product. So the dot product is a construction that can be made in Rn for any n. We're going to of course look at it mostly in 2 and 3 dimensions, but this is something that can be done in any dimension. And one thing that we'll kind of maybe emphasize before we do anything, one thing to kind of note is that the dot product is a number. Okay, so I'm going to tell you how this number is defined in a second, but I just want to emphasize this because one of the very common errors that people will make is they will assign some sort of vector quantity to a dot product. So a dot product is always a number. So the dot product is going to be something that you take two vectors as inputs and you get a number as an output. So let's see how that number is defined. So the dot product, it's also sometimes called the scalar product to emphasize the fact that the output is a number. The algebraic definition is this one here. So if I have two vectors, u, right, written in terms of its components, u1 up to un, v, written in terms of its components, v1 up to vn, the dot product of those two vectors is obtained by multiplying together the corresponding components. So I do u1 times v1 here, then I do u2 times v2 here, and so on until I run out of components. So I do this for each pair of components, right? And one of the mistakes that people will make is they'll take those products, u1, v1, u2, v2, and they'll write those as the components of some new vector. That's not something we're interested in. It's true that you can always form a new vector by just multiplying together the corresponding components. And that gives you some sort of vector product. The problem is it turns out that that is not very interesting or useful. So that sort of product, it just doesn't, it doesn't have a lot of useful properties. It doesn't have any applications. The dot product, on the other hand, we'll see that it's quite useful. So the important part here is that once you've calculated those products, you add them up, right? So you do u1 times v1 plus u2 times v2 plus u3 times v3 and so on. You add them all up. And so once you've added those numbers up, then what you're left with is just a single number. If you're comfortable with summation notation, then there's a short form here on the right-hand side. If you haven't really worked with summation notation, don't worry about it. You're not going to be expected to use it in this course. There is another way that you can define the dot product. If you think of two vectors geometrically, so you think of them as arrows, so things with magnitude and direction, u and v. So I can rotate my point of view until I'm sort of sitting in a plane which contains those two vectors, and I can kind of think of those guys as vectors in a plane. And if I think of them as vectors in a plane, then I can measure this angle between them. I can measure this angle theta right here. And we generally take theta to be sort of something, which is between 0 and pi, just to kind of resolve some ambiguity, because we don't want to kind of go the other way around. You can go the other way around. The cosine function sort of takes care of this anyway, but we'll generally measure the angle like that. And so you can measure the cosine of that angle between u and v, and we don't worry too much about. I should add, we don't worry too much about the direction of the angle here. The distinction is going to be between acute and obtuse angles. For something like this where you have an acute angle, we would want cos theta to be bigger than 0. If you were dealing with a situation where they were making some sort of obtuse angle, like so, then you would measure the angle this way, and cos theta would be less than 0. So there is the possibility that this dot product could be either positive or negative, depending on whether the angle is acute or obtuse. Okay, so the geometric formula says that you should calculate the length of v, then you should calculate the length of u, calculate the length of the two vectors, calculate the angle between them, measure the angle between them somehow, and then you can multiply these three together to give you the dot product. Of course, measuring an angle is not exactly something that's practical. You're not going to, probably be pulling out your protractor or anything like that. So what the way that this second definition is usually more useful is that, well, the first definition, this algebraic definition, is simple to calculate if you know the components. And so one thing this lets us do is, at least if our vectors are both non-zero, it means that it gives us a way of measuring the angle between vectors, because I can calculate the dot product. That's something that's easy to compute. I can calculate those two magnitudes. Those are easy to compute. And suddenly I have a way of calculating the angle between two vectors. And so this is one of the things that's sort of fundamental with the dot product, because the dot product actually, in one point of view, the dot product actually defines angles between vectors. So the dot product is encoding some of this geometry. Some of the directions are kind of built into this dot product, right? It's telling us how to measure angles, and to some extent it's also telling us how to measure length, because one of the things you might notice is that if you set u equal to v in this definition, you'd have u1 squared plus u2 squared plus up to un squared. So if you take the dot product of a vector with itself, what you get is the square of the magnitude, right? Cos theta, theta would be equal to 0 in that case. Cos theta would be equal to 1. And so there's information about the magnitude contained in the dot product. There's information about directions, about angles contained in the dot product. So the dot product encodes a lot of our geometry. Okay, so just to do a couple quick examples here, we'll do one two-dimensional example, we'll do a three-dimensional example. Let's do a two-dimensional example first. So in R2, maybe we take u equal to 3 minus 8. I'll take v to be the vector 2 minus 1. And so the dot product u dot v is simply, so we just multiply the corresponding components. So the 3 multiplies by the 2, and then we add, so minus 8 times minus 1, right? So we multiply the corresponding components and then we add. So 3 times 2 gives me 6, minus 8 times minus 1 is 8, and now I add them together and I get 14. Okay? And if I wanted to, I could also calculate the angle between these guys. I could compute that the magnitude of u is equal to the square root, so 3 squared plus 8 squared, so that's 64 plus 9. Well, okay, this is not going to be one that's easy to look up on the unit circle, but I suppose we could punch it into our calculator. 2 squared plus 1 squared, root 5. So if I wanted the angle between these two vectors, I guess we could say that the angle is 14 over root 73 times root 5. Something in principle you could use that to compute the value of theta. We're not going to bother to do it, obviously. In 3 dimensions, we can similarly do this sort of calculation. Let's say u is 3 minus 1, 5. V is maybe minus 2, 3, and 1. And if I calculate u dot v, I would get 3 times minus 2 plus minus 1 times 3 plus 5 times 1, right? So 3 times minus, here's my 3, here's my minus 2, those are the x components. Minus 1 times 3, those are the y components. 5 times 1, those are the z components. So I get minus 6 minus 3 plus 5. That comes out to be negative 4 in this case. Okay. So one of the things that you'd want to make sure, since we have 2 definitions of the dot product, you want to make sure that these things actually come out to give you the same number. Right? I gave you 2 definitions. How do you know that I'm telling you the truth, that these are both equally valid definitions of the dot product? Well, you actually just go ahead and you check and you make sure that it works. So the way you do this is, because you're dealing with just 2 vectors, you can assume that you're working in a plane, in a 2-dimensional plane. And so what you do is you draw things out like this. Here's my vector u, Okay, here's my vector v, and of course, I mean, a proof is, a picture is not a proof, but we'll see that you can use this picture to set up some algebra that works no matter how I actually choose to draw the picture. So what I'm going to do is I'm going to draw one more vector in here. I'm going to draw in this vector here from the tip of v to the tip of u, and what this vector is actually the difference. So if you've been practicing with your vector addition and subtraction by now and some of the geometric pictures, you've probably come across this, right? And so why is that red vector equal to u minus v? Well, notice that if I kind of add tip to tail, if I do this vector v and I add that to u minus v, well, v plus u minus v. Remember that vector addition is commutative and associative. I can change the order, I can move brackets. I can write that as u plus v minus v. V minus v, of course, is 0, so this is u plus 0. I get u, right? And so that makes sense. If I do v plus u minus v, that's the same thing as doing u. So that works out. So that's the vector u minus v. And I've got this angle theta sitting over here. So what I do is I say, okay, if I let a equal to the magnitude of u, and I let b equal to the magnitude of v, and I let c equal to the magnitude of u minus v, then the law of cosines says, well, the magnitude of u minus v, so u minus v, that's the side which is opposite this angle theta, that's your c, right? So the law of cosines says that c squared equals a squared plus b squared minus ab cos theta, and what you do is you plug things in, and the part you kind of have to notice, and we'll mention this on one of the next slides, you've got to play around with some of the properties. So c squared, that's the magnitude of u minus v squared. And the key to making this whole thing work is to realize that, well, as we mentioned on the previous slide, or maybe 2 slides ago, right, the dot product of a vector with itself, that's just the magnitude squared. So if I have the magnitude squared for u minus v, this is like u minus v dotted with u minus v. And we'll see that if you work through the algebraic definition of the cross product and you work through the properties that cross product satisfies, you can expand this thing out, and it turns out that what you get here is you get u dot u plus v dot v minus 2u dot v. Right, and so then this guy here is going to be a squared. This guy here is going to be b squared. Right, and then you kind of you plug all this into the law of cosines. The a squareds cancel, the b squareds cancel, and you're left with that 2u dot v. And actually, I've got to make a correction here. I'm missing 2 in my law of cosines. A squared plus b squared minus 2ab cos theta. This is the correct law of cosines. And you plug things in, and once you cancel, you're just left with 2u dot v is equal to, or minus 2u dot v equals minus 2ab cos theta. You cancel the minus 2's, and you're left with the result. Okay. So, in that kind of argument in favor of the two definitions being equal, I mentioned that there are certain properties that the dot product satisfies, and here are some of them. Maybe let's put some brackets in here, just kind of clarify things. So the order doesn't matter for the dot product. U dot v is the same thing as v dot, u. There we go. And the dot product is linear in the sense that you can distribute it over sums, right? So this, there's actually 2 kind of things here. One is that u dotted with v plus w is u dot v plus u dot W, so there's a distributive property, but also that if you have a constant inside, so if I have, like, say, A times V, you can pull that constant out. You can write that as A times U dot V. So you can pull scalars out. All right. The fourth property we've already mentioned, and this follows directly from the definition. And also, because u dot u, it's the magnitude squared. We know it's given by a sum of squares, and we know a sum of squares can never be negative. And we know also that the only way you can get that sum of squares to come out to give you 0 is if each one of the terms is equal to 0. So the only way that the dot product of a vector with itself can be 0 is if the vector itself is equal to 0. The last property, we won't worry too much about that, but one of the ways to kind of think about this is simply the fact that the absolute value of the cosine function is always less than or equal to 1. This is what you use to establish that fact. Okay, so these are all useful properties of the dot product. The other one that I should probably keep in mind is the following. Using the fact that u dot v is equal to the length of u times the length of v times cos theta, this tells you that if u dot v is equal to 0. So suppose you got the dot product of two vectors equal to 0. And let's assume that the vectors themselves are non-zero. So this is not 0 and this is not 0. I mean, that's one way that you could get a 0 dot product, right? If either one of the two vectors is 0, the dot product is automatically 0. But if those guys are non-zero and the dot product comes out to be 0, then what this would tell us is that the angle must be, well, cos theta must be 0, and that means that the angle must be a right angle. Theta must be equal to pi over 2. So we'll see in the next couple of videos that this is kind of the crucial property of the dot product. This tells us that the dot product lets us know when vectors meet at right angles. So if I have a vector u and a vector v, and they meet at a right angle, that's going to tell me that the dot product is equal to 0. And conversely, if the dot product is 0, well, either one of the vectors is 0 or they have to meet at a right angle. And so it's often important to know when two vectors are perpendicular in this sense. And so that's going to come up in a later video.